Hi everyone. This video is meant to be just a quick reminder of some things you've already learned about polynomials. And where this comes from, this is kind of going to feel like a hodgepodge, right? There's a couple of different topics that we're covering here. But we've taken a long look at the practice test for the SAT and tried to kind of come up with a list of topics that are very highly emphasized or topics that we see pop up a lot. And that's where this comes from. So we just want to review a few things with you, and then you've got some practice problems that go along with this video to just help you prepare, okay? So first thing is, when we're looking at the graph of a polynomial, these graphs look like all kinds of crazy things, all right? So this is just some random polynomial. They tend to be curvy, they tend to have all these bumps in them, but there's some pieces of this graph that we really care about a lot. First thing would be anywhere you have a bump, you've got an extreme value, a maximum or a minimum. This is going to be kind of a weird one here, but so I would refer to both of these things as relative minimums. If I wanted the overall minimum, if I was asking you for the minimum value, it would be this one here, right? Because that's the lowest one. Okay, and so this will have, coordinates to it, x comma y, something like that. And this one looks like it's about, I don't know, negative 1.5 and then negative 4 maybe. But one thing I did want to point out, because I've seen this pop up a couple times, be sure to read carefully. If they're asking you a question about a point like this, make sure you pay attention to whether it's asking you for the x value or the y value. All right. If it's asking for the x value, it's going to be pretty specific about saying what is the x value at the minimum. But if it asks you for the actual minimum, that would be the y value. This right here is the minimum value. That's the value of the minimum, and it happens to be located at x equals whatever. Okay, so just one thing you want to know there. And then, like I said, these things here would be considered to be relative minimums and maximums. I don't know that that's super significant. That is going to be something that's important when you get to calculus, but knowing locating minimum and maximum, you should be okay with. And then the other thing that we're typically concerned with are these points right here. Whoops, pen's not ready to go. These points, this one and this one and this one, which we would normally call the x-intercepts, right? We also know them as, let's see, I'll write this over here, either zeros or roots. Those are all the same thing. Zeros, roots, x-intercepts, okay? It's those circled points right there, okay? And this one right here is especially significant because the graph like touches the line, but it doesn't actually go through the line to the other side. So this is what's known as a double root. And when we get into the factor theorem, you'll see more about what that means. But the reason is, technically a graph, every time it goes through the x-axis, we expect it to kind of come out on the other side, right? So this went down below the axis here. It came back up again here. Normally, we would expect it to dip back down again in another location, okay? This time it didn't. It just brushed against it and then turned around. And so we count this as what's called, like I said, it's a double root or a multiplicity of 2, okay? Okay, and the roots are important because we have something called the factor theorem. And I could write the factor theorem out in words for you, but really I just want to write the relationship that it's getting at. Is if you know where the roots are located, so the roots would be at like x equals something, then you automatically know that one of the factors of that polynomial, and factors are things that multiply together to make something larger, okay, would be x minus whatever the number is, okay? And you can go back and forth between these two things. So if you know the factors, you can automatically figure out the roots. And if you know the roots, you can automatically figure out the factors. So it really depends on what the question is asking you for, but it's important to know this relationship. This is a really, really big one, okay? So just kind of looking back at my graph here, I have zeros at x equals negative 3. I have a 0 at x equals 2 and x equals 5. So if I wanted to write an equation for this polynomial, and we'll just call our equation, I don't know, p of x, okay? My factors would be x minus -3, which really turns into an x plus 3, okay? X minus 5, and then that double root, really what this means is that I have two copies of that. I have like x minus 2 and then another copy of x minus 2. So that's why it's important to recognize your double roots, because it means you have two copies of that factor. Normally we would probably just write this as x minus 2 squared, okay? But that's really what this polynomial would look like, all right? And depending on the problem, you may or may not have to actually multiply this all out, but that's the idea here, is that by knowing the roots, you can build the pieces of the polynomial, okay? Now, a corollary of the factor theorem, something that kind of goes along with the factor theorem, is something called the remainder theorem. The remainder theorem says that if you plug in some number into your polynomial, so p of some number, you plug that number into your polynomial, the number you get out will be the remainder. And I should have been more specific there. It's the remainder when you divide by that factor. Okay? And we're going to do some division down here, so you'll see what I'm talking about. But if I wanted to know, what is this whole polynomial, maybe multiplied out to standard form, divided by x minus 3, okay? So I could take that 3 and plug it in for x, and what that would give me is my remainder, okay? It's important to know, and this is how it relates back to the factor theorem, that if you plug a number in and you get 0, a remainder of 0 means that you're actually looking at a factor, all right? And so knowing that that thing is equal to 0 means that that number must be one of your roots, okay? So that's kind of how that all links together. I know that doesn't look, super clear when it's all written out that way, but when you do some problems that involve that concept, I think you'll see what I'm talking about. And like I said, we're going to get to some division in just a second. Okay, let's remember some factoring here. All right, and this, what I'm about to do, is eventually going to make use of this factor theorem up here that we talked about. But I've got this example here, x cubed plus 5x squared minus 4x minus 20 equals 0, and I'm trying to solve that thing. If it only had an x squared in it, if I only had that, I could do quadratic formula, right? But because of that x cubed, I really can't. So my goal is to factor this thing. Well, it doesn't have anything in common, right? Not all four pieces have any one thing in common, so I can't pull out a GCF. It's not a trinomial. It's not a difference of two squares. We'll have another video later on that'll remind you of all of our different types of factoring. But one that's kind of jumping out to me is grouping. I think that I could do some grouping with these numbers. So if I look at these two together and ask myself, what do they have in common? They both have an x squared in them. And then in parentheses, I'm going to say, what would they have left over? So if I took an x squared out of x cubed, I'd be left with x. And if I took an x squared off of that, I would end up with a 5. Okay. And then over here, if I look at these two, negative 4x minus 20, and ask myself what they have in common, they both have a negative 4. So then if I pull out that negative 4, I'd be left with an x. And then negative 20 divided by negative 4 is positive 5. So now I've got these two that match each other. So that becomes one of my factors. Okay. And my other factor comes from what's left over out here, x squared minus 4. Whoops. And this whole thing, I should have had this up here as well. This whole thing is still equal to 0 from up above. Okay, so from right here, we have the whole thing equal to 0. Okay, there is one more type of factoring I can apply here. I can split this up a little bit more. I can split it into smaller pieces. This x squared minus 4, That's what's known as a difference of two squares, and that's going to be an important one for you to be able to recognize. Anytime you've got a perfect square here and a perfect square here with subtraction in the middle, you can split this by doing the square root of each of those pieces, and one of your factors will be a plus and one will be a minus. So this will be an x plus 2, x minus 2, and then I still have my x plus 5 sitting here. So I've taken this cubic polynomial and split it into 3 factors. If I multiplied these 3 things back together, it would give me this. Okay? The reason that's important is because this thing is still equal to 0. Okay? And so if I know this is equal to 0, this times this times this equals 0. The only way to make that happen is for one of these pieces to actually be equal to 0. So now the question is just, what would make each piece equal 0? Okay? For this first piece, x plus 5, if I wanted that to equal 0, I would make x equal to negative 5. For this piece here, if I wanted this to equal 0, I would make x be a negative 2. And for this one here, if x minus 2 is equal to 0, x would equal positive 2. And this right here is that relationship that we were kind of talking about up here with the roots and the factors. Is if these are my roots, these must be my factors, or vice versa. If I have my factors, then I have my roots. So this right here would be the answer to my question. Okay, these are my solutions for x that would make this thing equal to 0. And if you really wanted to double check that, or if this was a multiple choice, you could take these numbers and plug them in up here for x and see which one equals 0. Okay, they should all equal 0 in this case. Okay, so that's a little primer on solving by factoring. As you factor it, you break it into as many pieces as you can, and then you say what would make each of these pieces equal to 0. Okay, let's remind ourselves how to do some division. And there's 2 ways that you can do division with polynomials. You can do long division or you can do synthetic division. I'm going to show you both here. For long division, let's say my problem was written like this. This is really this big polynomial divided by 3x minus 6. So I would write this with the 3x minus 6 on the outside and the long polynomial inside. So 6x cubed plus 15x squared minus 57x plus 6. Just a reminder to you, if you are missing any pieces in here, so let's say we jump from x cubed straight to x and we didn't have an x squared, you would want to put a 0 there to kind of hold that spot. Okay, so the first question I'm asking myself is 3x times what would give me 6x cubed? Well, I know I'm going to need a 2, right? Because 3 times 2 will give me 6. And then x to x cubed, I would need an x squared to make that happen. And now what I'm doing is 2x squared times 3x. That makes 6x cubed. It should make 6x cubed because that's how we set it up. And then I'm going to do 2x squared times negative 6, which gives me negative 12x squared. Okay, from here, I am going to subtract, all right? So now my goal is to do 6x cubed minus 6x cubed, so those cancel. 15x squared minus negative 12x squared. Remember, that's really going to be like a plus because you're doing minus a negative. So this would be 27x squared. And now I'm going to bring down my minus 57x. And now I start the process over again. Now I'm asking myself, 3x times what makes 27x squared? Well, I know I'm going to need a 9. And then x times x would give me x squared, so that's going to be a 9x. 9x times 3x is 27x squared. 9x times negative 6 is negative 54x. And once again, I'm subtracting here. So 27x squared minus 27x squared goes away. Negative 57 minus negative 54, which is really addition, minus a negative. So that's going to become a negative 3x. And then I'm going to drop down my 6 from way over here. And so now I'm saying 3x times what makes negative 3x? Well, that would be a negative 1. Negative 1 times 3x is negative 3x. Negative 1 times negative 6 is positive 6. And this time when I subtract, both pieces cancel and I'm left with a big fat 0. That's my remainder down there. That means that this divided in perfectly and that this is my final answer, 2x squared plus 9x minus 1. Okay? Now, depending on what the question's asking, you may have to do something else with that answer, but this is just the division process. Okay, your alternative to long division, especially on a time test, would be with using something called synthetic division. For synthetic division, it's important that you are using the root and not the factor. Okay, so what's the difference? Well, 3x minus 6, that is a factor, right? This is us saying that 3x minus 6 times this thing would give us back our original, okay? What we want to do is know what would the root be that's associated with 3x minus 6. And we find that by setting this thing equal to 0 and solving. So I would add 6 to the other side, divide by 3, and I get that this really represents a root of 2, okay? So if I was to graph this thing, one of its roots would be at x equals 2. So I'm going to set that 2 up in a little box over here. And then I'm going to line up the coefficients from my big polynomial. So I'm going to say 6, 15, negative 57, and 6. And then I'm going to leave a little space and draw a line underneath here. Okay? So the idea here is that I'm going to drop this first number down, leave it a 6, and then I'm multiplying. So 2 times 6 is 12, and then here I'm adding together. Okay? So 15 plus 12 is 27. Okay? 2 times 27 is 54, so 54 is going here, and negative 57 plus 54 gives me negative 3. Okay, and then 2 times negative 3 is negative 6, and negative 6 plus 6 is 0. And that's good because this here is my remainder this time. Okay, so that means this divided in evenly. Okay, now, why did we get a slightly different answer for this one? I'll show you that in just a second, but really what this represents now is the coefficients on my answer. So based on this, I could say this is 6x squared plus 27x minus 3. Okay? That would be my answer to this question. Now, the reason this didn't work out quite the same way as this one did, you'll notice this is like a multiple of 3. This is 3 times as large as the answer we got over here. When we set our root at x equals 2, by putting a 2 here, it's really as though we treated this 3x minus 6 as an x minus 2. Okay? We factored out a 3 to be able to do this synthetic division. Well, that 3 has to go somewhere, so that 3 ended up down here in our answer. Okay? So you would have to be careful with something like this, that you recognize that by making this a root of 2, that you're putting an extra factor of 3 into your answer here. Really, I probably should have just chosen a different example to do with this one, but wanted you to kind of see how that works. Okay, so synthetic division, long division. Okay, let's talk about what happens if you get a remainder, because we got a remainder of 0 on both of these. So back here, I have a division problem that's already been done. I was dividing x plus 1 into this polynomial. I got 2x minus 5 as an answer, but I have a remainder here of negative 1. Okay? A lot of the times we just wrote this as remainder negative 1, but I do want you to recognize the correct thing to do with that remainder. What this means is our answer here would be 2x minus 5 and then plus that negative 1 over the x plus 1. Okay, and actually, you probably wouldn't see this as a plus negative. You would probably see it written something like this. 2x minus 5 minus 1 over x plus 1. Okay, so if you were trying to do that division and it didn't work out evenly, first of all, that means this thing is not a factor. If there's a remainder, whatever you're looking at is not one of your factors. Okay, you don't know what is a factor, but you know it's not that. But this would be the correct way to write your answer. And I have seen a lot of SAT problems that involve this remainder here. So I want you to recognize when you see something like this, and you know that it was originally looking like this thing here is representative of a remainder. Okay, I think that was everything I could think of for polynomials right now. We may need a little bit of practice with some factoring, but other than that, you should be okay with the polynomial section for your SAT review.